Hello, this is Dr. Oz. Today I would like to talk about linear optimization models. And these models can be used for support and improve managerial decision making. Okay, so the idea here is to make better decisions using data, and these models can support and improve managerial decision making. There are two different types of objectives in these models. Either they are maximize good things or minimize bad things, right? Maximize or minimize functions. And these are called objective function. Okay? And these functions should be maximized or minimized based on set of rules. We call them in modeling constraints. These are the set of rules and regulations, okay? Constraints. All right, so let's go to introduction, talk about some typical applications. So we can use these linear programs in manufacturing settings, for example, production scheduling. How many products shall we produce each day, each hour, each week, so that we achieve our goals. We can decide on inventory policies. How many shall we order? What kind of products should we order? How often should we order? What is the reorder point kind of questions. Financial analysts use optimization models, specifically linear optimization models, quite a lot to, for example, manage their investment portfolio. How many Apple stocks should they buy? How many Google stocks should they sell? Should they hold any Amazon stock? If so, what percentage of the portfolio? How often do they make these buy and sell decisions based on what factors? So these are important considerations, and linear optimization models are very handy. Also, marketing is a really hot topic that they use optimization models a lot to allocate the fixed advertising budget, for example, choosing the means of the advertising channels like web, radio, television, social media, and so on. And also, for example, Amazon uses optimization models, linear optimization models for their warehouses. How should they organize their warehouses? How many locations should they have? What should be those locations? Which location should serve which customer? So these are very important questions for companies, and linear optimization models can help companies to answer these questions. Okay, so let's give an example here, a simple maximization problem. Again, we are trying to maximize here good things, positive things like maximize profits, maximize sales, maximize income, maximize companies' life expectancy, could be examples. So let's talk about problem formulation and mathematical model for PAR Inc. problem, okay? All right, so in the next slide, let's talk about the PAR Inc. Corporation. This is a small manufacturing firm producing golf equipment and supplies. And their market, they would like to move into medium and high priced golf bags. So this is more like a marketing decision. They would like to get into new segment, medium and high priced golf bags. And parts distributor to buy all the products by the end of the third month. So their distributor would like to buy their products at the end of third month, and now the company needs to decide on the decision making variables, so that I'm going to talk about. So what are they trying to achieve here? That's an important question for a modeler to think about. All right, so to be able to produce their products, looks like they have two different types of products, standard bag and deluxe bag. And there are some requirements for these bags. For example, to be able to produce one standard bag, they need to have 7/10 of cutting and dyeing department hours, or half an hour of sewing, and 1 hour of finishing, and 1/10 of an hour in terms of inspection and packaging. The same corresponding numbers are given for deluxe as well. So each product is requiring different amount of hours. Again, here I'm just giving you an example of maximization problem. This is this problem could be expanded into different areas. Okay, I don't want you to just think that this is a manufacturing problem. I can use the same logic, linear optimization model for different settings. All right, so let's see. Obviously, we don't have infinite number of hours available for us in each department. For example, in cutting and dyeing, we have only 630 hours available for me. So if I think about 40 hours a week for one employee, for 1 month, that employee will work 4 times 160 hours, right, per month, 160 hours per month. So that means that I have here 4 employees. One of them looks like doesn't work all the time full time, but overall around 4 employees here. So maybe I'm using that employee sharing with other products as well. So every standard bag that I produce, I make $10 margin, profit margin, which is revenue minus expenses. Probably this doesn't include fixed costs. We will talk about those in another chapter, fixed costs and variable costs. And if I sell deluxe bag, I make only $9 per unit. So if you look at these two numbers, you may say, hey, why don't I just produce standard unit because it gives me a better profit margin? Yes and no, because yes, $10 is greater than $9. However, we need to consider how many can I produce? How many standard bags can I produce? And how many deluxe bags I can produce in a way that I will maximize my overall profit? All right, so this is an important consideration. You cannot just look at the profit margin and say, hey, I will produce only standard bag. So as I told you before, we in optimization models in general, linear optimization models specifically, we should have constraints. In this case, these rules or regulations, for example, cutting and dyeing time available. We don't have unlimited time here, all right? Another constraint here, second constraint, is sewing time available. So each department has available time. Since I have 4 departments, I have 4 constraints associated with them because I don't have infinite number of hours available for me. So let me go to the next slide. I would like to talk about decision variables. So again, it's important to note that every optimization model have 3 components. One, objective function, which is either a maximization problem or minimization problem. In this case, we are trying to maximize the profit. So this is a maximization problem. This is the first component of our optimization model. Second one is the decision variables. In other words, what are we trying to decide here? Decision variables. Third one is rules and regulations. In other words, constraints. Okay, what are the constraints that I have? In this case, I have 2 different decision variables. I would like to denote them by S and D. S means number of standard bags, number of standard bags produced, and D is number of deluxe bags produced. Okay, deluxe bags produced. All right, so then the objective function has to have these decision variables in it, and as I told you, to say maximizing the good things. So in this case, I'm trying to maximize the overall profit. So how can I measure profit in this case? 10 times S plus 9 times D. So what is 10? Profit margin for standard bags. What's 9? $9 per deluxe bags profit margin. So coefficient times the number produced. Let's go to the next slide. So let's talk about the constraints. As I told you, there are 4 departments and 4 constraints. So the first constraint is obviously I have 630 hours available for me in cutting and dyeing department. So every single constraint has, by the way, 3 components. 1, left-hand side values. 2, the relationships. 3, the right-hand side values. So the left-hand side values are calculations. The relationships here could be less than or equal to, greater than or equal to, less or greater or equal to. Those are all possibilities. And right-hand side values in general, they are given to us. These are constraints right-hand side. In this case, I am given that I have 630 hours available in cutting and dyeing department. And also it was given in the slide number, in this case, what's the number here? 6, I believe. That I if I produce a standard bag, I need 7/10 of an hour, and if I use deluxe bag, I need 1 hour. So if I plug in those numbers, 7, 10, and 1, so this is how my constraint looks like. So 7/10 of an hour times the standard production amount, right? That's our decision variable. Again, decision variables has to be in your constraints as well as in your objective function, plus 1 times deluxe specs production. So 7/10s plus 1d should be less than or equal to 630. If I do the same thing for sewing department, so my right-hand side value is I have 600 hours available. Again, you can check those up there in the previous slides. And the relationship is less than or equal to, because I cannot spend more than 600 hours, and every standard bag require half an hour times S plus 5/6 times D. All right, so that's my left-hand side value for this constraint. So again, this is my constraint number 1, this is my constraint number 2. So if I talk about the third constraint, which is associated with finishing time, my right-hand side value is again given to me as the what is the right-hand side value? That's given to me as 708 hours available for me. Again, this is less than or equal to constraint. So on my left-hand side, I know every standard bag will require 1 hour of finishing department, and plus 2/3 of deluxe production amount. Okay. Again, these parameters, these are called parameters or coefficients. They are given to me as well. All right, and these are right here, S and D, as we defined before. These are my decision variables. So let's go to the last constraint here, which is constraint number 4, inspection and packaging time. So I have 135 hours available for me. So I can spend maximum that much. That's why, since I can go up to that much, I use less than or equal to constraint. And I need 1/10 times S, and I will have 1/4 times D. Okay, so is that it? No, because programs or models are not super smart like human beings. So I need to tell them exactly everything. So in this case, what I need to tell my computer is that another constraint on top, let's say 5, is that S, which is number of standard bag production, should be greater than or equal to 0. I cannot produce negative number of bags, obviously, right? And also same thing for deluxe bags. It has to be greater than or equal to 0. So we call these our non-negativity constraints. So they are really important to include in your model. So if I summarize the model in the next slide, so I have, again, 3 components, right? First one is the objective function, which is maximize 10s plus 9d. Of course, the more I produce, more profit I would generate. And then I need to talk about the constraints, right? Constraints, which is subject to, I abbreviate as SD, which is 7/10 S plus 1D is less than or equal to 630 hours for cutting and dyeing department, 1 over 2s plus 2 over 3d less than or equal to 600 Rs for sewing department. Third constraint was 1s plus plus 2 over 3d. I have a I think typo at the top. Let me just correct this carefully. Let me delete this. So this coefficient for the finishing department was 5 over 6. 5 over 6. All right. So for finishing department, 1s plus 2 over 3d should be less than or equal to 708 Rs. And finally, inspection and packaging, I have 1 over 10s plus 1 over 4d should be less than or equal to 135 Rs. And plus, we talked about s and d has to be greater than or equal to 0. All right. So this is my model in high level. All right. So let's go to next slide. Here, this model is called linear programming model or linear program because the objective function is and also constraint functions are linear functions. What do I mean by that? Look, so this is your objective function, and as you see here, this is a linear function. You don't see squares, you don't see ln's, you don't see sinus, cosinus, and all this fun, crazy equations. So this is linear, and all these constraints here, as you see, they are also simply linear functions. You don't see square terms or power 3, 4, 5, whatever. So this is a linear function. But by definition, linear function means that as a mathematical formulation in which variables appear to be in separate term, raised to power first. So nothing like this or that or this, right? These are not linear functions. These are harder to solve. These are not regular linear functions, okay? All the power should be 1. Okay, so that's it for today. We covered a simple maximization problem today. And next time, I would like to give an example and solve a problem with you guys in Excel. See you next time.